Hello friends, welcome. So today I'm going to discuss about damped oscillations, and if you are interested then only watch this video. So first let us talk about damped oscillations. What are damped oscillations and how they can be used in the electrical systems. So let us first talk about damped oscillation. So here you can see a ball. This is a ball of a massive ball. It is having some mass. It is a spring. A spring is attached to this ball, and this spring is pulled by a distance of x from the equilibrium position, such that the spring would experience a force in the upward direction, which is the kx. The ball would experience a force in the upward direction, and due to this viscous liquid, the viscous fluid, it would again experience a force in the upward direction, which will be proportional to its velocity, cv. So now we have to write the equation of motion for this ball. Writing the equation of motion for this ball, we have to consider the Newton's second law. So let us write the equation of motion for this ball. So here from Newton's second law, we can write ma plus kx plus cv is equal to 0. And once you write it in the differential format, it would be m d2x by dt square plus k plus c dx by dt plus kx is equal to 0. Now this is a differential equation of second order. Now let us see that how we be solving this equation. So you don't need to know that how we would be doing it, you need to know that what we would be doing. So here the general solution of this equation is e to the power lambda t. Okay, so how to find lambda? So once you substitute this in this equation back in this equation, you substitute this back in this equation, we will be getting a very amazing result. So here first we will be substituting it. So we'll get what m first we will try to substitute it. So differentiating it two times, we'll get m d2x by dt square. So e to the power lambda t derivative taken with respect to t is lambda e to the power, so m lambda square plus k lambda, sorry, plus c lambda and plus k is equal to 0. So this is the equation. Now because e to the power lambda t would get cancelled and k would be remaining, so this is called the auxiliary equation. What is this? This is called the auxiliary equation. Now the next and important thing is m lambda square plus c lambda plus k is equal to 0. Now we'll be finding the value of lambda, so we can write it as minus c plus minus root c square minus 4mk by 2m from the Sridharacharya formula. Now here we will be considering three cases when c square minus 4mk would be greater than 0, c square minus 4mk would be less than 0, and c square minus 4mk would be equal to 0. Now these three cases define three different types of oscillation. So this is called underdamped. This situation we say it as underdamped oscillations. C square, when it is equal to 4mk, we say it is a critical damping. It is critical damping. Now C square, it is called over damped oscillations. Okay, now we should talk about another important thing, which is called the coefficient of damping. So let us denote the coefficient of, let us write about the coefficient of damping. So the coefficient of damping, the coefficient of damping could be written as gamma, which is c by 2m. Now what is c? C is this. Suppose I write gamma critical. So I would be writing c, which is equivalent to the critical value, which is c is 2 root mk by 2m, and this would give me root k by m, which is gamma critical. Or we can also say that we saw this type of critical in the case of critical damping. This was equal to omega of a simple harmonic oscillator. You remember it? omega was equal to k by m. That kind of oscillations are taking place here. So this is equal to 2 root mk by 2m. Now this is the value of uh, critical damping coefficient. So the next important thing is we should be talking about under damped oscillations basically and over damped oscillations. So here you can see the graph of um, x over x naught. Now what is x naught here? X naught is any general position of the ball. Okay, so here x naught is any general position of the ball. So this is x naught, and x naught, x by x naught is any general position of the ball. So here you can see that there are different kinds of graphs shown. So this graph is called the over damped condition. What was the over damped condition? When c square minus 4 mk was greater than 0, this was called the over damped condition. So here when the c square, the underdamped, now we need to talk about the underdamped equation. The underdamped response of the oscillator is described by the equation this. So we need to basically talk about underdamped conditions and underdamped oscillations. So these oscillations are overdamped oscillations. Now this one you can see just below the overdamped curve, this is the critical damping. Critical damping. So critical damping is somewhat like this. This is the over damped and this is the under damped. Okay, this is the under damped. Now again you can see this one, this curve which is just below the critical damping curve, this one, this curve is one half of critical damping. This is one half of critical damping. Now this curve which is the longest curve here, you can see it has the highest amplitude. This is 1/10 of the critical damping. Now, where is underdamped oscillator? So, whenever an oscillation goes below the critical damping, it is called underdamped oscillation. As you can see, this one is 1/10 of critical damping, which is also an underdamped oscillation. So, any type of oscillation which is just less than the critical damping or critical oscillation, that kind of oscillation is called underdamped oscillation. I hope you all understood this. Now, the general equation for the underdamped oscillator is x is equal to e to the power minus lambda t, where lambda is the coefficient of damping, a is the amplitude of the motion, this is the harmonic function, and this is omega 1. Now, omega 1 can be written as omega 1 minus okay, basically we have to write it in the terms of omega, where omega is the natural frequency of the system without any kind of resistive force. So we would be writing it. Now we already know that whenever the value of the coefficient, this is the coefficient, the damping coefficient, whenever the value of the damping coefficient gamma is less than the critical value, it is called gamma of underdamped condition. And whenever an upper limit exists, it is called gamma of overdamped condition. Now all the curves, as you can see here, which are lying below the critical damping curve, this curve is lying, these two curves are lying below the critical damping curve. One is one half of critical damping and one is 1/10 of critical critical damping. In both these cases, the value of gamma is less than that of gamma critical. That's why these cases are called the underdamped oscillations. These are called underdamped oscillations, and these oscillations are called overdamped oscillations. So as you can see, here is the graph, and there is always a damping present. Okay, so this is e to the power minus lambda t, and this curve which is sinusoidally decreasing, it is always lying below the curve. So here omega 1 could be written as omega naught square minus gamma square. What is omega naught? Omega naught here is the frequency of the system without any damping force. So omega naught, where we would take it out as common, and 1 minus gamma square by omega naught square. Now here omega 1 can be written as 1 minus c square m by 4m square k. Now here we will be writing we will be simplifying it, so we'll write omega 1 is equal to omega naught c square 1 minus c square by 4m k. Now omega 1, when it would be equal to omega naught, when this term would tend to 0, c square by 4m k, when it would tend to 0, will be getting omega as approximately omega naught, omega 1 as approximately omega naught. And when this would happen when c square is very less than 4 mk. Now this is the condition when the motion will not be a damping situation. Now we will be considering the same with an LCR circuit. Now let us talk about an LCR circuit. It's a very important portion, and for that only I have just discussed all these things. So let us talk about an LCR circuit. Either you can take it with a charged capacitor, or either you can take it with a battery, external DC source. I would be considering the case of charge capacitor, and you try to do it with the help of battery. So here is L, R, and C. This is a switch. It is having a charge of Q naught plus minus. This is having a capacitance of C. It is an inductor of R and R. Now we have to write the equation for this loop. So writing from the Kirchhoff's loop rule, I can say that once I traverse in this direction, I can say uh, L di by dt plus I R plus q by c is equal to 0. Now why I am writing q by c? I am writing this because first of all, let us write the differential equation in a more elaborate manner. So I suppose a q charge leaves this plate, and current I flows in this direction. So the inductor would behave as a battery of this much EMF, and it would be behaving as plus minus also. So here I will be writing L d2q by dt square, which is di by dt, plus I, which is dq by dt, r, plus here you can see that once I close this loop, now this is traversing from this direction to this direction. Now this is q naught minus q by c is equal to 0. This kind of equation is forming, and it is also similar to the above kind of equation. Now here we can say that why it would execute a damping type of condition, why it would have a damping, because in an LC circuit we say that E initial is equal to E final, there is no energy loss. But when we introduce a resistor, and a resistor is when introduced, the circuit becomes a damping circuit, because the resistors loses energy in the form of heat. So we can say that this type of circuit would have a decaying current. This kind of current it would have. So we'll be writing it as L di by dt plus IR plus. Now here you can see we are entering from the minus side of the capacitor. On the minus side of the capacitor, we can write it as minus Q naught minus Q by C. Now we'll be writing it as 0. So this is L d2q by dt square plus I, which is dq by dt r, minus and here I can write it as plus q minus q naught by c is equal to 0. Now substituting q minus q naught is equal to qc. Here I can write it as d2qc by dt square L plus dqc by dt r plus qc by c is equal to 0. Now this equation is a type of equation that we already dealt above. Now here at that time the position was a function of time and it was a decaying exponential function. Now here the QC would be a decaying exponential function. Now here QC can be written as maximum amount of charge. Okay, QC could be written as a to the power minus gamma t gamma t, and then we'll write it as cos omega 1t plus phi. Now here gamma for this circuit could be written as c by 2m. Now c by 2m here is r by 2l, r by 2l. So here qc could be written as a q sorry a to the power minus rt by 2l cos, and here omega 1 is equal to omega naught, which is 1 by root lc. Now what is omega naught? Omega naught is 1 by root lc, and into 1 minus we'll be writing gamma square by omega naught square. So gamma square is r square by 4l square, so it would be r square c by 4l and 1 by 2 of this. So this is cos omega 1t plus phi. Now here I would say that initially when the circuit was an initial time here t could be written as 0. At time t equal to 0, the charge in the circuit q was 0, and similarly the current in the circuit was 0 at time t equal to 0. Now we'll be using this to find some important things. So here qc, the value of qc that we already assumed to be q minus q naught, q minus q naught is equal to a to the power minus rt by 12 cos of omega 1t plus phi. Substituting all these values here, we'll get q, which was 0, minus q naught is equal to a to the power 0 cos phi. Now here we can say that similarly the current would get current by differentiating this value. We would get current by differentiating this, so we'll be doing that here. Okay, so here we can say that, okay, so q naught minus q naught is equal to a cos phi, minus q naught is equal to a cos phi. And once we differentiate this, once we differentiate it, we'll get a to the power minus lambda t, and cos, we'll get the value of current, the value of current, and you can try it by your own. So here you'll get the value of phase constant, and omega 1 has been given, and you can see that here the charge would always exponentially decay resulting in a graph like this, and one it would terminate. So this would be e to the power minus lambda t, and it would always go below it. So this kind of charge is here. So let us analyze the situation. So here energy was the charge was traveling through the inductor, and when it passes through the resistor, it started losing energy in the form of heat. That's why when the charge loses energy, uh, the current slowly start to decrease, and once it terminates. So this was all about damping oscillations and how we can consider them in an LCR circuit. I hope you like the video, and let us also analyze the situation for the ball. So here you can say that the ball, let us talk about the ball. Here the ball was having an energy in the upward direction. Let us say this is half kx square. Now half kx square is sorry, the energy has no direction. The spring has a stored energy half mv square. The ball was moving downward, it was having a stored energy of half mv square, and due to the cv, it would be cv dx type of force. Integrating it, we will get the value of the work it done, work it did. And I don't know whether this type of conservative or non-conservative force, but we'll try to find the work done by this situation, and then we'll also analyze that how the heat losses are occurred in this situation. So I hope you like the video. Thank